This is Official Nerd Business.
Hello nerd boys and girls, welcome back to our programming series, and we are taking a second look at Project Euler's problem 24. Recently I posted a video where we tackle the part of the problem. The problem is about permutations, so in what order can we arrange elements from a list, and when we do this exhaustively and order them, then what is the end combination of elements on this list. I made a video discussing the theory behind it, behind how the patterns appear in those kinds of listings. And today we're going to work that out in a working program. So as you can see, I've already opened up my editor here and I have made a Euler24.py. I've copied in the problem statement from Project Euler, and we're going to make this a little bit prettier by adding one or two line breaks. Wait, that was the wrong button. There we go. Good enough. So here's the example case again with all the permutations of 0, 1 and 2. And we are requested and required to find the millionth lexicographic permutation on the digits 0 through 9. So yesterday we had a look at the theory behind it, or in the other video, link in the description, obviously. And today we're going to take a look at the actual programming. Now I've set this up with my regular test method with A, B, C and D as used in the other video, and also an entry point for main pi to call this one. And attempt number 1, this will simply be a call to our permutate function, and in permutate all the magic's gonna happen. I've taken this out of attempt number 1 because this is pretty obviously the sort of function that we want to incorporate into our lib Euler. Permutations might be something that we'll see in the future, and then we just want this in our library. Now I've not placed it in our library at the start of this, at the start of coding it, to give us a chance of testing it locally in this file with calls like this. You will also notice that on the line where we specify parameters, there's two of them. There's the list, and it is of type list, and for that I made a little change in main.py. We'll take a quick look at that. As you can see, the default expression for this list is a list comprehension. And in main.py I've looked at the part where we interpret the inputs, and here is a little if statement that checks if the type is int, then we just make an integer out of it and pass it along. And now we do have an additional type list here, and I call eval. Eval looks at this text value, because q at this point is a string to Python, and it will execute the code as if it were Python code. Now since it contains a list comprehension, it actually is Python code, and executing it will give us a list with the elements 0, 1, 2 all the way up to 9, and we assign that to q. So q now has a list, and then q is appended on the list of instantiated parameters, and then we call the program with the inserted. So there's a minor change in main.py. You might want to write that one along when you're following this. Also, link in the description to my GitHub page where all my source code, including main.py, can be found and copied from if necessary. So that for main.py, that for two parameters. Note the separator char we have here, the backtick we have here between two parameters. I tried to use a tab sign in the past, but tabs got eaten and replaced by spaces, so that was suboptimal. Yeah, so let's get right into it. Right off the bat, we have a function here that takes the given index, and we have a list of values. And we saw yesterday that there were a couple of edge cases that we want to take into account. In this case we want to return simply the empty list. If we get only one element in our list, then we want to return the list itself. And if we have two elements, if we have exactly two elements, then we want to return let's see, first we want to make x to be the given index modulo 2, just as a shorthand. And now we want to return list x plus one minus x. Let's make lists out of this, because when you use the @ sign on lists, and let's explicitly make lists out of this, if these are string elements, you use the plus sign, then the Python will simply add up to string values, and you will get the concatenated string out of it. That's not what we're after. But if you use, I also could, by the way, use this slightly simpler. But what we are going to use is that plus sign for lists. And if you have a list with, say we have a list L1 with the elements A, B and C, and we have a list 2 with the elements D and E, excuse me, there we go, then this is a list with all the elements concatenated in one single list. So that's a principle we're going to use a little later on. But first we're gonna fiddle. We had an f value, right? And the f value was set to let's have an import statement here. We had the f as maximum number of possible values, and this was possible number of ways in which we can arrange objects is, let's take any one element of our list times, so that has n possibilities where n is the length of the list, times let's take the following element of that list, which is n minus 1 possibilities, n minus 2 possibilities, etc., until we have only one possibility left. So that's n factorial, and where n is the length of the list, the number of items on our list. And if we saw that if the index was greater than this possibility, then we could do we could set the index to be the index modulo f, clamping the index within the range of possibilities. We also had a g, and the g was equal to this minus 1, and this value describes how many possible tails there are for any chosen element at the head, and this was used to calculate our slot values, and the slot value in this case is the cast2int of our moduload index over not Q but G. And now we in fact simply want to return a list containing the popped element plus a call to ourselves with the same index and the same list. Note that this list value now is being altered by the pop. When we call pop on this list, the if we use the string ABCD, and we determine here that we should be looking at the 0th element in that array, then this will be 0, and list.pop will be abcd.pop, giving us A. A is put into this list definition and leaving the list BCD. So A is no longer part of the original list. A or pop modifies the list to no longer contain the one element popped. So that's pretty that's tricky. You should be very well aware of that. Alright, so this should do the trick. We are going to test it on ABCD. It doesn't yet run anything, of course. So we need to return permutate on the given list and the given index. Okay. Oh, we do have an error somewhere. I think at some point we switch up as I've switched up the arguments here. That's a fun one. So the permutate function expects an index and a list. Would it be more intuitive if we required a list and then an index? So feed it a list and an index, alright. Oh, right. It's occasionally, most of the time, strings will be handled as lists, but not this time. And I bet if I did that wouldn't work, but this might. Alright. No, it doesn't. Let's just write it out then. A, B, C, D. Oh, another twist up. When calling this function recursively, I accidentally still had the instructions, the arguments in the wrong order. There we go. DBCA should be the 22nd permutation in the catalog of all the possible permutations of A, B, C, and D. There is, however, one thing. I said we would run into practical problems, and that is the following. If we were to do this, we should get the same result. Why? Because the results should be either alphabetically or numerically ordered. So if our inputs are the same, though not in the same order, but the same elements, then our results should be the same. If we were to run this program, we now get a different result. As you can see, I got DBCA and now I have DACB, so that's not right. But how can we make it right? Well, we could obviously, when we haven't quit early, so like right about here, we could say that the list is oh, hang on. And now we do get the same answers, but there is something slightly off with this, and that's that the list gets sorted now every time we run this, and on smaller sets that might not matter, but I'm worried that this might cause performance at some point in the future. So what we're going to do here is we are going, when this is called, we will sort the list once and then defer the rest of our execution to an inner function. So we have functions here, and these functions might contain functions of themselves again. Those functions are invisible to the rest of our code. So if we enter the list and index here again, we can now call this function from within the body of the permutate function, but we cannot call it from any other function. As you can see, autocomplete does not complete, so that's a pretty dead giveaway that this is not something that the Python compiler is very happy about. And what do we want this function to do? Well, in fact, just everything that the up until here outer permutate is doing for us. And then this should call itself again, though as inner permutate. And this way we can guarantee that the list gets sorted only once, and then execution is deferred to the inner method, and the inner method knows that it's also always working on a sorted list. So we want the list in there in the index. I'm going to give this a test run. And we get the results that one would expect. So here's our permutation function. It's it has the corner cases for 0 and 1. It sorts the input. It then constructs the necessary output with one default breaking case for when there are only two options left in a list. And it will call itself time and again. It will make sure that whatever it is called with falls within the range of possibilities. It will remove one possibility from the phase we saw in the other video, and then it will run this very merry loop once again until it hits this particular case. Keeps on adding items to its own tail, and then returns. Then sees what it already had stored, sees what it gets back from the inner call, then returns, etc. all the way back up until this one returns the actual data back up to here, if it didn't quit early on one of these edge cases. Sure, it looks great in theory, but does it work in practice? We're gonna find out. Let's start at main.py. '24. Default parameter is this list comprehension. Default lookup parameter is 1 million. And then we get an error. That's a shame. So I had to cut out for a second to find out what the actual issue was. It was a new one for me, and I've made a dry run of this problem. So which is kind of weird. I think it's a conflict in the way the parameters from main pi are passed into this Euler 24 problem, where on the first run this is seen as a string, and then this isn't a modulo operator but it is a string formatting option, and it was the error was for an unrecognized formatting option, or for the fact that not all parameters here were strings or something along those lines. So explicitly casting this to a numerical value got rid of the error. So we are going to run this now. And we run 24 with all default parameters, and we get the number we should concatenate. The end result should not be a list, but it should be a number. So we will do this. Join is a function that you can use on a string. You feed it a list, and then it will combine all the list elements with the string in between. And in this case, we provided the empty string. We could do this, and it would put in dashes, but we don't want that. We simply want all the numbers to be glued together without further white space. So there we are. This should give us the result we want. And oh great, it doesn't work on lists of integers. But we can remedy that easily enough. And there you go. If you enter this number over at projecteuler.net, you will not get the green check, you will get a red cross. And why is that? And we are off by 1. And as said before, these indexes are the index into the permutation catalog 0 based. We get the 1 based value off of the description in on Project Euler. So the actual value we are looking for is this one under 1 million. So if we were to run this instead, and there is the correct answer, and it's super quick. All it really does is concatenate a couple of lookups into a origin list to figure out the order of things. So all in all, programming wise, it's once you've figured out how what the magic trick is, programming wise this one is pretty easy but fun to do. And it's good to take a look at inner functions. We haven't seen those before, at least not far I can recall in this series. So there's a very useful feature that protects us from, that gives us a bit of scoping. So we can do some prep work for permutate and then leave all the recursive calling once that prep work is done, especially this one and these two edge cases. Since this prep work is done, we can forget about it and simply run the inner permutate until we have a result and return that. Thanks for watching. I'll see you again for problem 25. Oh, wait, no, don't go yet. I have a bonus challenge. With all the coding we've been doing up to now with the permutation function, can you create a program for me that lists out all possible permutations of any given collection? So if I were to give your program A, B, C and D, could you list out all possible permutations using this function and all the knowledge that we've built up around permutations? Post a link to your answer in the comments. Thanks for watching this video on Official Nerd Business. Don't forget to like and subscribe and click the bell icon. Did we discuss everything you wanted to hear, or did we miss anything? Any topics you want to hear in O&B? Leave your thoughts in the comments. See you next time.